Bismillahirrahmanirrahim. Today we will go through the resin modified glass ionomers and related materials. If we want to introduce these things, that what are these materials, that if we have a look towards the properties of restorative materials, then it reveals that no single material from composites or glass ionomer is suitable for all applications. So the selection of material will be more difficult, and decision is much difficult, and a dentist should go and thoroughly evaluate the limitation of the products, the composite and the glass ionomers. As we people studied in glass ionomer cements, that we have combined two materials, the glass ionomer with amalgam, and a new product is produced for better properties and for the use of that material, where the original glass ionomer material not work efficiently. So a hybrid type material, which is called as cermet, was evaluated with most advantageous properties of those material. Was produced which overcome or which has less disadvantages of the glass ionomer cement. So if we are going toward the blending, then apart from the amalgam, there are other things which are closely related to glass ionomer. So why they should not be tried? So early attempts produce hybrid products involve blending together components of commercially available glass ionomer and composite material. So this material was not viable as a clinically usable product, but possibility of combining these two, this similar material, is possible. Then further research and development was done, and a new family of materials with a diverse in nature and composition, a different composition which lies somewhere on the continuum between resin matrix type composites and acid base reaction type component. Resin matrix mean composite and the acid base mean are glass ionomers. At one extreme of the continuum, we can view these products as composite material in which a modified resin and a reactive glass have been used. And at the other end, they can be viewed as acid-base cement matrix products with added resin. One is closely matching with the composite, and the other is closely matching to the glass ionomer. Now the figure in the book will give you some indication of the material which lie on the continuum. Figure also indicates very approximately the nature of the materials in terms of the relative contribution of cement or resin matrix, from which it is possible to develop a profile of expected properties. This is the figure. Material is composite, and advantages: composite is strong, tough, insoluble, radiopaque, and quick setting. Disadvantages of composite that it has no inherent adhesion, polymerization shrinkage is there, and no fluoride release. Now comes the glass ionomer. Inherent adhesion, little shrinkage, fluoride release, and biocompatible. These are the advantages. While disadvantages are brittleness, solubility, radiolucency, wear, water sensitivity, and slow setting. Now you can see the continuum, that this is the resin component and this is the salt component. That is pure composite, compomer, giomer, resin modified glass ionomer cement, and pure glass ionomer cement. Now, composition and classification. Much controversy over the terminology was there. So, ISO standard 99172 for light activated water-based cement describes the product as water-based and setting by multiple reactions, which includes an acid-base reaction and polymerization both. An attempt has been made to further subdivide products in these categories into modified composites and resin modified glass ionomers. Variation on these materials occasionally produce other new categories. One example being the giomers. These new categories often turn out to be very similar to one of the existing group. Giomers are very similar to the modified composites or compomers. Now, modified composites, resin matrix composites in which usual inert fillers has been replaced by an ion leachable aluminosilicate glass, which are present in glass ionomer, in order to encourage fluoride release. But no acid-base reaction takes place during the setting of these materials because resin matrix composite, all we know, have a setting reaction of free radical polymerization type, obviously of methacrylate groups, and usually these are light activated. Chemical activation is also there. In some materials, resin, in addition to the normal dimethacrylate components, also contains acidic, normally the alkenoic groups, in order to generate the possibility of an acid-base reaction with the glass component. These products are often referred as acid-modified composites due to the replacement of dimethacrylate component with the alkanoic group component. The compomer has also been used to describe these products. These acid-modified composites are also termed as compomers. The primary setting reaction is still through polymerization of methacrylate group in the resin component. Only the dimethacrylate component is replaced. The acid part of modified resin is unable to enter into an acid-base reaction with the glass due to the absence of water, as no component of this material having water. Now, if we go for the application, most widely used material from this categories are supplied pre-mixed in small syringe, single dose syringes. Modified resin and glass are pre-mixed and stored in the syringe before use. So, water should not be there. If water is there, there is a chance of premature setting. So, water is not added in this. So, again, incorporation of water also prevented by packaging these syringes in a waterproof foil container. And after setting through polymerization, it is considered that some acid-base reaction can occur as the resin takes up water and the acid group become ionized. So this process may enable the surface of the glass particle to react in order to liberate fluoride also. So a compomer or acid modified composite material is supplied like this one. And single tube, single dose syringes, also called as compules, and directly you can inject this material into the cavity by using this device, this gun, and this material then sets by light source. Now available materials, modified composites, number of components are 1 or 2. Required mixing 2 component, yes, if 1 component like in compomers, no mixing is necessary. Active ingredients are fluoroaluminosilicate glass, methacrylate resin, acid modified. Sorry, resin modified glass ionomers, again 2 components or 3 components may be there, requiring mixing. Obviously 2 or 3 components if there, then it requires mixing. Fluoroaluminosilicate glass, methacrylate, polyacid, hydroxy, ethyl methacrylate, HEMA, water and activator, initiator, stabilizer. And then comes giomer. Giomer is available only in single component. So no mixing is required as it is in a single paste form. Again, active ingredients are aluminosilicate glass pre-reacted with polyacid dimethacrylate resin matrix. Now these geomers, these are similar to the acid modified composite except that the acid base reaction is completed before blending the filler with the resin. Here the acid base reaction has been completed before blending the filler with the resin. The aluminosilicate glass is reacted with polyacid in order to form a pre-reacted glass polyalkenoate complex. Now, 2 distinct products are produced. As we reacted the product before blending. So first is known as surface reaction type. It involves the breakdown of only the surface layer of the glass particles. And the second one is known as full reaction type. It involves almost complete breakdown of the original glass particles. These 2 types of geomers. Following this initial reaction, the product is ground and blended with the dimethacrylate resin to form a composite structure. Now, the reaction products prominent feature of the full reaction type is that some hydroxyethyl methacrylate HEMA is required to enable mixing of the hydrophobic resin with the fully reacted glass. As we all know that hydroxyethyl methacrylate or HEMA having the difunctional molecule, so it enables mixing of hydrophobic resin with the fully reacted glass. Principle of the formulation and manufacturing process is that fluoride is released from the glass particles during the acid-base reaction, and when the glass polyalkenoate complex is blended with resin, the fluoride become available for release. In the surface reaction products, only the surfaces of glass particles are consumed. And for these products, the mechanical reinforcing effect of the filler particles is given priority over fluoride release. Fluoride release in the surface reaction type is less. For full reaction products, fluoride release is prioritized at the expense of mechanical properties, while in full reaction type, the mechanical properties are lower. Both the full reaction and surface reaction type products are provided to the dentist as a single paste material already described, which set through light activated free radical addition polymerization reaction of meth acrylate group in the usual way. Now, resin modified glass ionomers. These products are considered by some authorities to be more truly based on a hybrid of two parent groups of material. In their simplest form, they consist of a powder and liquid, which require mixing prior to activation of polymerization, as often these are through light activation. Most convenient of the restorative type resin modified glass ionomers are provided in an encapsulated form, in which the powder liquid ratio is determined by the manufacturer and the mixing is carried out mechanically in only a few seconds, like in glass ionomers encapsulated form. The powder consists primarily of an ion leachable glass, and the liquid contains four main ingredients. And these are: number one, a meth acrylate resin, which required for the polymerization and setting. A polyacid to initiate the acid base mechanism and reaction with ion leachable glass. HEMA, hydroxyethyl methacrylate, which is a hydrophilic methacrylate and enables both the resin and acid component to coexist in aqueous solution. HEMA also takes part in the polymerization reaction. And water. Water is an essential component required to allow ionization of the acid component so that the acid-base reaction can occur. So this is the giomer, single paste presentation, a syringe. The name is reactmer. And this is a resin modified glass ionomer material, powder and liquid. These are present in this container or capsule, in this pouch, where a capsule which can be mixed as we have mixed the glass ionomer, or as we have mixed the amalgam. And again, this can be extruded through this tip directly into the cavity. Again, the mode of activation is light polymerization. This is the reaction, resin modified polyacid chain through esterification, polyacid HEMA, and this is the resin modified polyacid chain. Other components, minor Other components are activators and stabilizers. Some products have a simple formulation through blending polyacids and dimethacrylate in aqueous solution. Most products have special formulations, especially for resins, where both methacrylate and acid groups are present as active groups on a single polymer chain. And this can be achieved through this polyacid hema. Some of the acid group on the polyacrylic acid molecules replaced with methacrylate groups by carrying out an esterification with hema. This is the reaction. Now, reaction powder and liquid component of the cement when mixed, acid-base reaction begin immediately as acid group are able to react with the glass in the presence of water. So powder and liquid, liquid usually containing water. Polymerization takes over as the primary setting reaction as soon as sufficient free radical becomes available to initiate the reaction. If it is a chemical cure type. If it is a light cure or light activated product, this corresponds to the time at which the light irradiation occurs. The light source used to activate polymerization is of the same type as that used for light activated composites. Polymerization involves the pendant methacrylate groups of the modified resins along with any free hema and absorbed water or any free hema which have absorbed water. For giomers, already explained that acid-base reaction have been completed before blending of the glass polyalkanoate complex with resin. Now, dimensional change and dimensional stability. All categories of materials discussed in this chapter undergo a significant shrinkage on setting due to the resin part. The major component of the shrinkage is due to the polymerization of methacrylate group in the resin component. Acid-base setting makes a minor contribution to the observed shrinkage. The magnitude of the shrinkage is similar to that observed for resin matrix composite. And the same arguments about shrinkage stress or shrinkage stress, cavity size, and configuration factor apply to this also. Water absorption. Resin modified glass ionomers undergo a rapid and marked expansion when placed in water. And this expansion is more than which compensates for the shrinkage and even can result in the material protruding from the cavity and exerting a positive pressure against the cavity walls. This observation can be explained by a value of water absorption after 7 days of 100 to 25 micron gram millimeters cubic millimeter compared with the maximum of 40 micron gram cubic millimeter per cubic millimeter allowed for resin based material in ISO 4049. Large value of water absorption for the resin modified material is due to the use of the hydrophilic monomer, which is HEMA, hydroxyethyl methacrylate, as the primary constituents in these products. The clinical significance of the observed swelling is yet to be fully explained. That is not clear. Swelling does not occur to the same extent with modified composites, as these products generally do not contain HEMA. The full reaction type geomers contain HEMA and they have a very high value of water absorption. Radial pressure. Effect of radial pressure generated by water absorption of these products is likely to depend upon the stiffness of the set material and the cavity configuration, the C factor. It is conceivable that the expansion and radial pressure generated within a low stiffness material may have a beneficial effect in helping to seal the cavity margin because it presses, it goes outward and it can seal the cavity margins. In high stiffness materials, water absorption is likely to produce high radial pressure, which could lead to excessive pressure on cavity walls. The effect will be magnified by a high cavity configuration and would be particularly concerning for luting applications where cements are constrained as thin films with very high configuration factors. Now the mechanical properties, flexural strength values of a range of resin modified glass ionomer and modified composites are given in table 25.3. Along with the minimum values required in the ISO standards. You can see there. If possible, I will show you. It is clear that whereas some of the weaker resin modified glass ionomers are only marginally stronger than the conventional glass ionomer products, some of the single component acid modified composites have a strength value which clearly satisfies the requirement of ISO 4949 for resin based material. Later products compare favorably with composites. The values given in table 25.3 support the hypothesis that the material have a structure or property characteristics which would place them somewhere on a continuum which connects the purely acid-base reaction material at one extreme and the purely resin matrix product at the other. In general, incorporating increasing amount of resin in a glass ionomer system seem to have the effect of strengthening and toughening these otherwise brittle materials, as the glass ionomer is a brittle material. But as we all know that resin modified not the resin modified glass ionomers, the resin or resinous materials become weaker after a period of water storage. So likely the resin modified glass ionomer becomes weaker after a period of water storage. So as they have a large water absorption, values. So modified composites appear to be relatively unaffected by water storage. Now, this is the table 25.3. Flexural strength is at 24 hours of resin modified requirement of ISO 99172 and ISO 4949. Flexural strength was recorded at. Resin modified glass ionomer component 2 and 3. Mixing, all we know require. Flexural strength is 25 to 60 and 65 to 80. Three component having more flexural strength. Modified composites, two component, again requiring mixing, and if a single component, then it will require no mixing. So two component having 35 to 40 megapascals and single component having 100 to 120 megapascals. And these are the compomers. Now giomer full reaction type, as all having both geomers are single components, so no mixing required. Full reaction type having already described low flexural strength. Surface reaction type having more flexural strength. Requirement of ISO 99172 and 4049. 99172 is 20 and 4049 is 80. So most of these except these two are near to these values. Now adhesive characteristics. All materials, इसको क्या हुआ आज, कभी ओढ़ा कभी नाच रहा, क्या हुआ इसको? All material within the group of resin modified glass ionomers and related products contain polyacids of various types and at varying concentrations. So all materials therefore have a potential to interact with the tooth surface to produce bonding as for glass ionomer cements. However, the magnitude and efficacy of the bond is often limited by one of the following. Number one, lack of sufficient concentration of free acid groups to form an effective bond. Lack of sufficiently ionic character to enable bonding to occur. Lack of mobility of the active acidic species to enable interaction with the tooth surface. Some of these materials, despite having the potential for bonding, require the use of intermediary agents or primers in order to achieve effective bonding. Now, dentine conditioning. Some of the products within the resin modified glass ionomer groups give an inherent adhesion to enamel and dentin by a mechanism which is similar to that for conventional glass ionomers. Free polyacid groups are thought to interact with the mineral of the tooth surface. When no conditioning or etching is used, shear bond strength of 4 to 10 megapascal to both enamel and dentine are claimed for some products. Improvements in bond strength are obtained when enamel and or dentine are etched or conditioned, and most manufacturers advocate the use of conditioners such as aqueous polyacrylic acid in order to remove the dentine smear layer. If you people having difficulty in understanding this conditioning and conditioner and smear layer, etc., you can go to my lectures on bonding and for glass ionomer cements. In these lectures, there we have explained it in much details. The priming. Other manufacturers, sorry, other manufacturers advocate conditioning and priming of dentine and enamel prior to placement of the restorative material. Primer may be a solution of the methacrylated polyacid, one of the major ingredients of the liquid component of the cement, which is able to partly demineralize the surface of the hard tissue and leave a surface which is more readily wetted by the restorative material. Thus, use of conditioning and priming can increase the shear bond strength into the range of 8 to 24 megapascals. Priming also described in detail in the chapter of adhesion, adhesives and adhesion. Modified composites and geomers. Now, previous discussion revealed that some materials must be treated in a similar way to composite in order to achieve an effective bond. That is, special treatments of the enamel and dentine are required in order to produce effective bonding. To achieve adhesion with the modified composites, products, they must essentially be treated as composites and bonded using adhesive bonding agents similar to those described in section 23.8. For geomers, there are insufficient quantities of accessible acid groups to enable effective bonding to occur. Dentine and enamel bonding systems similar to those used for composites must be used for these. Fluoride release as a major advantage of the conventional glass ionomer, but studies demonstrated reduced levels of demineralization and carries around material which are able to release fluoride ions in vitro. The pattern of fluoride release for conventional glass ionomers indicates a high initial release rate followed by a rapid reduction in the rate of release over time. The relative importance of the initial burst of greater level of fluoride and the sustained release at a lower level over an extended period has not been fully explored. Level of fluoride release required to produce a therapeutic effect are not known, and in the absence of such information, it is often assumed that greater level of release are better, whereas this may not be the case. The top up, one factor which may be significant in the fluoride release from conventional glass ionomer is reversible. And when these materials are bathed in an environment containing a high fluoride concentration, for example, a topically applied fluoride gel, they are capable of taking up fluoride. Following such treatments, the fluoride release rate of these cements can be significantly increased as they are able to slowly release the freshly absorbed fluoride. It is therefore said that conventional glass ionomer can act like a fluoride sink, which is capable of releasing fluoride, but which can be topped up at regular intervals. So this is the picture daily, that is mean 24-hour fluoride release over time, and topical glass ionomer. Now fluoride release microgram per millimeter square, time of days. If we see 50 days, 100 days, 150, 200 days. Maximum it is, if we see, release is about, if we see there, it will be 1 day, 24 hours. So at the first day it will be 1.5 micron gram per millimeter square, and initially after some time it will be 1, after 2 or 3 days it will be 0.5. So the solid line is for glass ionomer cement. You can see much more release of ionomers, fluoride. Dashed line is for resin modified glass ionomer, and dotted line, this is for the compomer, modified composites, etc. So you can see the much lower level of fluoride release with compomers or resin modified composites. Now the pattern, 24-hour fluoride release of small specimens of cements 10 millimeter diameter by 1.5 millimeter thickness into 5 ml of water as a function of time. Storage water is refreshed throughout the test. Results show that typically the resin modified glass ionomer behave in a similar fashion to the conventional glass ionomers in terms of both the pattern of release and the daily amount of fluoride release. Fluoride released. It is emphasized that results are for typical materials and some considerable variation is seen between commercial materials. Key factors in the rate of fluoride release from resin modified materials are the extent to which the acid-base reaction occurred during setting and the presence of HEMA, which results in the formation of a polymeric hydrogel through which water can diffuse quite rapidly. Fluoride release behavior of the modified composite product is somewhat different to that of the other material. Now the sustained release, there is no initial burst, but there is a low and sustained level of fluoride release, which typically after about 40 days becomes equivalent to that from a conventional glass ionomer. After 40 days, they all will be same. You can see, except the compomers. Now, lower level of fluoride released from these products is a function of the limited extent to which any acid-base reaction occurs, combined with the lower rate of water diffusion through resins which do not contain the hydrophilic monomer, that is HEMA. Smart behavior already described in the previous chapter of glass ionomer. Fluoride release from geomers is comparable to that from acid modified composite. Fluoride available for release is that which is liberated from the glass during the initial reaction with acid prior to blending with resin. Hence, the fully reacted glasses produce products with significantly greater fluoride release than the surface reacted glasses. Further, the presence of HEMA in the fully reacted glass products facilitate more rapid diffusion of water and fluoride through these materials, as HEMA is hydrophilic. The modified composite materials and geomers may have an ability to be recharged with fluoride in a similar manner to that described for conventional glass ionomer. This may be another example of the potentially smart behavior of material with some glass ionomer structure. The rate of release, effectiveness of fluoride release as a form of prevention or protection is a matter of some debate. After the first few days, initial fluoride burst, which is seen for conventional glass ionomer and some resin modified material, the rate of release become very low and it debatable whether this long-term release can be beneficial. However, a sustained long-term release promoted by a continual release, recharge and re-release may well provide the positive therapeutic effect which dentists require. Hence, it is likely that the long-term pattern of recharging and re-release is much more important than the high initial release. On the other hand, there is some evidence that the material which have the greatest initial fluoride release also have the greatest ability to be recharged. Now, the pH fluoride release of material changes in response to changes in pH. Lower pH generates greater levels of fluoride release, and this may be another example of smart behavior because now this material show smartness of coping with the high acidic content. Since the benefit of fluoride is particularly required in regions subjected to plaque acids, mechanism of fluoride release at low pH is likely to involve some dissolution of the material, and so the increased fluoride release may be at the expense of material durability and longevity. Now, clinical handling notes, handling characteristics and clinical techniques used for these materials are different to those for the conventional glass ionomer cements, not least because they become hard as a consequence of the visible light activated reaction well before the acid-base reaction is completed. Matrix techniques are similar to those used for composites and discussed in the chapter of composites, with transparent cellulose acetate or polyester strips on proximal surfaces. Again, cervical cavities pose a problem because of the need of transparent matrix to permit light activation. One possibility is to use a small piece of kitchen film, cling film, as a physical separator that will allow contouring using hand instruments prior to light activation. These materials are not susceptible to desiccation as the chemically setting types, and consequently surface finishing can be undertaken immediately after placement of these materials, not like the glass ionomer cements. And thank you very much for your patience. Needs your comments. Waiting. Allah Hafiz.